I could spend a lot more time on number theory and cryptography and cryptanalysis as a subfield of abstract algebra. It is best left to its own course. And courses in number theory are much more broad than just what we looked at with our little bit of the RSA algorithm. Instead, I want to focus on actually something that sounds like I'm moving backwards. We were talking about solving equations. And that's how we got into inverses and how we got to that. But let's go back to generalizing that idea. Polynomials. I'm going to define the set of polynomials with coefficients in a ring as R of X, where the X is in square brackets. Now, X itself is not part of the ring. X is an indeterminate, a variable. And that's because it's quite easy to write an equation whose coefficients are in one ring that has no solutions in that ring. So X itself isn't part of the ring. It's a separate idea. So I don't have equations. And that means instead of trying to solve an equation, I really think about factoring, which is what we could be doing when we think about our polynomials over any ring. I want to think of factoring instead of solving. And in a sense, this goes back to our homomorphism theory, when we were trying to find the evaluation homomorphisms, phi sub a, of a function that would give us 0. You've seen this crap before. Even if we go to the most general case, this looks like Calc 2. And so our ring of polynomials can really be written like power series. A0 plus A1x, A2x squared, A3x cubed, and on and on and on. However, AIs are not allowed to go on forever. In a power series, AIs could be non-zero all the way out. Here I'm saying only finitely many of the AIs are not 0. In other words, at some point there's a highest power of x, and everything after that is 0.
What's that little bit after AI?
R, 0. So if I say like, the last non-zero AI is A100, then I have a polynomial of degree 100, right? But that means everything from 101 on. Well, that's when the shipping trucks go back and forth. Everything from A101 off to infinity is 0. That means that this is really a finite length object. Power series are technically infinite. Okay. We will think of a function as an element of our ring. We'll call the AI the coefficients. And I'm going to use all the same terminology we've used in algebra all of our lives. The value of n so that m equals 0 for all m bigger than n. The highest number, that's our degree of our polynomial, and the coefficient an is called the leading coefficient. Interestingly enough, this is a problem because if the polynomial is all zeros, the zero polynomial itself, that's true for every n, isn't it? So technically, I would be able to say that starting at 0, a0 is 0, a1 is 0. That means that this value of n that I am using should be negative. There are no negatives up there, are there? Doesn't make any sense to do that. So when you think of the polynomial that is 0 everywhere, it technically doesn't have a well-defined degree. Some textbooks will say, oh, that's degree 1 because it's a constant. Sorry, degree 0 because it's a constant. And 1 is degree 0 and 2 is degree 0, but this is somehow worse. Some textbooks will simply say, no, degree is undefined, we're not going to bother with it. And that's because the other way to define the degree is to say it is the power for which an is not 0. This doesn't have such a thing. We're in an arbitrary ring. Our coefficients are in some arbitrary ring R, which means that ring could be any kind of ring. It could be a ring without a unity, like the even numbers, right? If it is, I just can't write x squared, because there's no 1 to go with it, right? If R has unity, then I will allow myself the statement, oh, you don't have to write a 1. But if R doesn't have a unity, I'm in trouble for that. But that means I could write equations, I can write polynomials in any ring at all, right? all of these have integer coefficients. However, these two, well, actually these three, are technically not factorable over the integers. Kind of iffy with the constant, but definitely the middle two, F and H, I can't factor those in the integers. Which means there's solutions, if we even agree that how you solve these things makes sense, aren't part of the ring. That's why the indeterminate is not part of my ring. Questions so far? All looks really familiar, I understand that. Okay. Here are two just now made up polynomials. I want to define operations. How do I add polynomials?
Just add both together.
How do I add? By adding. I need you to be a little more precise than that, please.
I mean, like, I don't know, if you have like x squared and 2x squared, or just you add up the coefficients of the, you know.
There's a phrase here you're skipping over because it's blanking in your head. But yes,
Like terms.
like terms. Combine. Okay. So whatever's xi on that f, whatever's xi in g, I'm just going to add the coefficients. So I can write this as the sum. I goes from 0 to infinity. AI plus bi, x to the I. I gathered my like terms. Ben, same idea. I have 4 questions. Is the set of polynomials closed under this operation? It's that time of the semester. Why, Ben?
Because additions are even.
That's not the question I asked, unfortunately. I do want to know that later, but for the moment, I just want to know, is it closed?
Assume they have a unity.
No. Can't assume anything about my ring.
I mean, if you add two polynomials, you still get a polynomial.
If there's some highest term for each of those, then the highest term that's not 0 here will be whichever of those is higher. So this is still an element of Rx. So we're closed. For the addition operation, got closure. Going all the way back to section 1. What else do I need? I want to show eventually this is an abelian group. What are my other 3 things for a group? Associative,
Distributive.
that's for a ring, not for a group.
Identity.
Identity,
Inverse.
inverses. So, how do I get there from here? I need to show this is associative. Wait a minute. R is a ring, not Rx, but R itself is a ring, right? So, if I think of f of x plus g of x plus h of x, I will just now make up h of x as ci x to the I. Let's put parentheses in two different places and see if we get the same thing. Actually, let's just show we get the same thing. You want to do f and g first or g and h first? That's what my associative rules tell me to do, right? So that would be f plus g is this, ai plus bi, x to the I, plus h. And then that is parentheses ai plus bi plus ci on the outside, x to the I equals 0 to infinity. Yes? That's the way the addition is defined. You take the coefficient from the first one, add it to the coefficient of the second one. R is a ring. A, B, and C are elements of a ring. What does that tell me about the addition for those things? All of this working with regular numbers has gotten you unused to doing proofs again, huh? Hasn't it?
To show that's associated.
But in the ring, in any ring, the addition forms an abelian group, right? Which means I know in the group R, not Rx, just R, this is already associative. And now I can uncouple my addition. I can uncouple A from the B and C. And then I can uncouple these. Well, that's F plus G of X plus H of X. And look, the parentheses are now on the other side. Our addition is associative in Rx. It's closed. It's associative. Is there an additive identity in Rx? Ah, the one we called Z of X equals 0 for all x, if you add that to a function, you're going to add the coefficient 0. That doesn't change anything. Perfect. Do I have additive inverses?
Just make a polynomial with like the negatives. Use coefficient.
Then if I add f and g, I get the 0, which is our identity. We have identity, inverses, we have a group. And now, because why is it abelian?
I'm going to just say that we know addition is abelian.
In what?
And we're using integers as coefficients.
I'm not necessarily, I'm using R as coefficients. Like R could be any ring. No?
I was just gonna say, like, you just said, like, in a ring, I was just gonna say, is, like, when it's in a ring, it's abelian, the addition is abelian.
Because in every ring, the additive thing forms an abelian group, right? So I can say, hey, let's add two polynomials. But because I'm in a ring R, this addition is abelian. And that makes the addition in the polynomials abelian. So here's the problem, and I think it's catching several of you, but Reese, I think this is exactly the issue in general. R is any ring. I could, if I really wanted to, make rings whose coefficients were polynomials themselves. I could make rings whose coefficients were matrices. I could make rings whose coefficients are weirdest. That's strange. So how do I make this work properly? I need to look at the coefficient behavior separately from the polynomial behavior. So I've got two different additions here. I've got the additions in the coefficients, and I've got the additions in the functions. So the addition doesn't exist. Which addition am I talking about? Okay, great. It is an abelian group. Set of polynomials is an abelian group because I have an addition, satisfies all my properties. Chef's kiss. I really want to make it a ring. But to make it a ring, I need another operation. I need my multiplication.
Is this in the same problem or a different problem?
No, same problem.
Okay.
Because my goal is to say polynomials are rings, but in order to show that this is a ring, I got to first show it's an abelian group under the addition. Then I have to show the rest of the rules for being a ring. But in order to show that there are rules for being a ring, I have to have a second operation. So here's my question. How the hell do I multiply polynomials?
By the like terms.
I multiply, because you're familiar with that, I understand what that means. And we think, if I multiply only like terms, all right, wait a minute. If I multiply like terms, then 1 plus x times 1 plus x, I multiply the 1 and the 1 and I get 1. I multiply the x and the x, I get x squared. Is that right? In every algebra class in the country, that's going to get me in pain. So I can't just multiply like terms. Ian?
Do we have to multiply every term by every term?
Which is what you meant by just multiply, right?
Yeah.
Which is really what rule? Distributive property on steroids, right? How many of you have seen lattice multiplication? Gather my like terms. The way I was taught lattice multiplication is that you don't put the vertical one on the left, you put it on the right. And then everything shows up in the right order when I go down these diagonal lines. Yes? So what happens when I do it for those? I'm in trouble. This is going to be an infinitely long multiplication, isn't it? But let me just do the first three on each side. End up with that. And now I have to go and combine all my like terms, yes? So just for the constant x and x squared, combine your like terms. What do we get here?
I have a question.
Yes.
before we get to that. How do you know you're using like A1x, AX2, like an onward from the
Because up here we said that f was aix to the I and g was bix to the I.
Yeah.
So I'm just using these.
continues?
Right.
Yeah.
But I only just wrote down the first three for each of them for the moment.
Yeah.
I could write down as many as you want.
Yeah.
It's just going to take longer. And I didn't see a particular need to do more than three. We should do x cubed, but we'll do it after. Show you why x cubed. What's the constant term?
B0, B2.
That's it, right? That's the only constant term up here. Linear term.
One B0 times A0 B1.
Those are added.
Yeah.
Right? I'm gathering my like terms. Those are added together. These two. My quadratic term.
A2 B0 plus A1 B1 plus A0 B2.
What do you notice about the subscripts in each case?
To the power.
Yeah. 1 and 0, 0 and 1 adds up to 1. 2, 0, 1, 1, 0, 2 adds up to 2. What should be the coefficient for x cubed? It should be all the different ways to add up to 3. Now, rather than write the a coefficient big and make it go small, I'm going to write the a coefficient small, let the b's go big. Where have I seen this before? Algebra class, Calc 1 was a long time ago, man. We did x plus h to a power. In Calc 1, right? We did the binomial expansion. Remember how to expand a binomial? Problem stats people, you remember the binomial coefficients? N choose k? Y'all were here for this. I didn't make this up. And what happened to the powers of x's? They started out high and they got lower. And the power of h started out low and got higher. These coefficients are doing exactly the same thing in exactly the same way. So I can define multiplication to give me a new series where CK is itself a sum a K, a K minus N. Not K minus N, N minus K. No, K minus N. I did write it down right. So when I do 3, we go from 0 to 3. A0, B3. We've done part of it right. A0, B3, A1, B2, A2, B1, A3, B0. But really, this is the distributive property on steroids. If I want to show that the polynomials make a ring, what's the next thing I have to show? The definition. Show the group part. What's next?
Works for 2 operations.
What works for 2 operations? What properties have to work when I deal with both the operations?
Associativity? We need to prove for this as well.
I don't need to prove the multiplications associated. I need to prove the distributive rules. I need to say that F times G plus H is FG plus FH. And I need to show the multiplication on the other side, that G plus H times F. But since this multiplication is defined in terms of distributing, I don't need to reprove distributing. Yay! Do I show multiplication associated? Now I'm stuck remembering my properties of my rings. I have to show, have an abelian group, closure. You only have to show unity if you want to get a ring with unity, but for a general ring, show the distributive properties. Do I have to show the multiplicative associative? When in doubt, go look up the properties of a ring. You all have your notes in your books. Find it. Chapter 17. 18, somewhere back at the beginning of rings. A ring R with 2 operations plus n times.
Our addition is an abelian group.
We did that part.
Multiplication is associative.
Crap. That's the part I have to do that I haven't done yet. Multiplication associative. So I was wrong, Ian, you were right. I have to show multiplication associative. Sorry, I screwed it up. All right, how do I fix this? I have to show that when you do that twice, it multiplies out correctly. So I'm gonna get A times B times C, and they're gonna be interleaved like that. I would love to say that that follows automatically from the ring itself being associative, but it doesn't, because our multiplication calls all these regroupings. I really should do this long, ugly-ass calculation. I'm not going to from the textbook. It does work, but it is just, 8 miles and 20 minutes worth of me writing down the same crap 3 different ways. I think it's on page 220-ish in the book. Okay. Mia, after associative, the only other thing that was left was the distributive property? Great. I've shown everything I need to. If the ring is commutative, then so are the polynomials. What's a commutative ring? What's it mean for a ring to be commutative?
It's abelian.
Groups are abelian.
Multiplication is commutative.
So abelian only applies in this case to the additive part. If I want the multiplication to behave that same way, that's where I'm using the word commutative. So commutative ring refers to the multiplication being reversible. Okay, reorderable. If my ring is commutative, then the polynomials are commutative. If my ring has unity, then my polynomials have unity. And it's the same element. Whatever the unity is in your ring is also the unity in your polynomials. On the other hand, a number of my other things I would like to say should generalize fail to, for some very weird reasons. A couple of examples. D2x. Remember I told you you couldn't do this? Why can't I? This works perfectly. Why does this work? Because I'm in Z2. And I take all my coefficients, mod 2. When I get that 2x in the middle, that's 0x. Woo, it's gone. You ready for me to get even weirder? That's true. Why?
Maybe one's one mod two.
Same exact reason. I'm working Z2. Now, if I change that mod even slightly, rules change substantially. In Z3, x, one plus x times 1 plus x is 1 plus 2x plus x squared. But 1 plus x times 1 plus x times 1 plus x is 1 plus x cubed. Because it should be 1 plus 3x plus 3x squared. But there ain't no 3 in Z3. Questions? Takes getting used to. There's no question about that. It does. Everything we do here for one variable holds for more variables. You can have polynomials that are multivariate, which is what Calc 3 is all about. So I know the things exist. All of the same rules and same proofs apply to do f x1, x2, or r x1, x2, or z3 x1, x2. What's an integral domain?
Delivering with unity one is not equal to 0 and it has no zero divisor.
Ah, no zero divisors. Having no zero divisors is a critical piece there. Now, we said that every finite integral domain was a field. So the only integral domains that aren't fields are infinite ones. We haven't done too many of those. So for the moment, let me think about fields. It would have been so nice. It would have been so bloody nice if f is a field and f of x is a field, but that's not true. Why not? What makes a field a field? which means every element has a multiplicative inverse, right? I am going to give you an element of polynomials that has no polynomial inverse. Ready? What do you multiply that by to get 1? But is 1 over x a polynomial? No, it's not x to some positive power series, is it? 1 over x is x to the minus 1. That's not an element of our set. There's no multiplicative inverse there. It has a multiplicative inverse, 1 over x. But even back in my very first algebra class, what did we call functions where we used division? X squared over 3x plus 2, x squared plus 2x plus 1 over x cubed minus 7x plus 15. What do we call those? Chapter 3, section 3 in the calc book where we did the product rule and the quotient rule. We only use the quotient rule on quotients, right? We gave those kinds of functions a name. They were something functions. I hope not, because we didn't use that word ever again. What's the set Q called?
Rational.
The rational numbers for the rational functions. That's the problem. 1 over x is not a polynomial, it's a rational function. It's a different set. So I can't have it in the same set. It's not a field. That's why we need the quotient rule for it. Or the extension to the power rule. Okay. I said I wanted to talk about factoring rather than talking about solving equations. But I did say that solving equations was related to homomorphisms earlier, didn't I? So let me take two fields. F is a subfield of E. I hope it's abstract you guys keep texting about all day. I can define for an element of E, the bigger field, the map phi alpha from polynomials whose coefficient are in X to E. By evaluating. This is a homomorphism. Not an isomorphism, definitely not one-to-one, undoubtedly not onto. So it's only from f of x into E. We call this the evaluation homomorphism. Valuation at alpha. The entire rest of this course, the entire rest of this subject is based on figuring out how this homomorphism works. We are in chapter 27 in our textbook. There are like 60 chapters in this book. The remaining 33 are dealing with this and its consequences. This is the reason this subject exists, is to study and understand how this homomorphism works so that we can figure out how to solve equations properly. The whole purpose of algebra is solving equations. If I ask you to plug in 0 to f of x, what do you get out? Always? Remember, f is any polynomial.
That's b f of 0.
Yes, well, what is that in terms of f? Okay. Say the same thing.
Would that be based on whatever polynomial?
Yes, but I can be much more specific than that. I can say, hey, my polynomial, remember f of x looks like this. I'm going to put it as 0 for every one of those x's. What happens?
The whole thing is 0, right?
No. The whole thing is not 0. Almost all of it is 0.
For, let's say I, is going to spit out whatever the last, whatever x of, like AI x of 0 would be.
That's f of 0, yes. But it's ai, it's going to be a0 x to the 0, right? So it's just going to spit out a0. In other words, when you plug in 0, you get the y-intercept of your graph. The constant term out of your polynomial. That's the only one that doesn't have an x on it, right? Everything from here on out gets blown away to 0, except a0. Now, I can then say, oh, all the functions that have a y-intercept of 0 are in the kernel of this homomorphism. So solving an equation is a matter of figuring out which evaluation homomorphisms is that function in the kernel. For the moment, I'm going to use a field, right? Because E and F had to be fields. So I'm going to use the field Q. And I'm going to go to R. The real numbers. Because every rational number is real, but not every real number is rational. Well, let's call this G of X. X squared minus X plus 6. G of X is in the kernel of phi 2. Yes or no? Is G of X in the kernel of phi 2?
Yes. Because if you like put in 2 for all the x's, you get 4 minus 2 plus 6, and that's
4 minus 2 plus 6.
never mind. I'm bad at math.
But if I use that one, then it works, right? Finding solutions is now changed to finding out what homomorphisms contain the polynomial in its kernel. I could literally spend an entire second semester working through the theory of kernels to get to what polynomials can be solved easily and what polynomials can't be solved easily and why. However, there are 3 days of class left after today. I don't have a whole nother semester to do the entire rest of the book. But this is where this goes. My goal now is to say, all right, what can I figure out about these homomorphisms? What works the way I want it to? If I'm in Z5, factoring works. Because Z5, 5 is prime. That's a field. Turns out, the factored version of this polynomial is this one. Which, by the way, is the same as this one. Why? -4, +1 are congruent. By the way, jump back to discrete again. Again, I'm using a field, right? QX. If I were to ask you to solve this, you would tell me that the roots are
Minus square root of 2.
great. I claim the square root of 2 isn't a rational number. That in the field QX, sorry, in the integral domain QX, this can't be factored. And you did this proof in discrete, where you proved to me that the square root of 2 is not a rational number. Got to write down the kernel here. Not an element of the kernel for any of them. And we know that's true because we know how to show that the square root of 2 is not rational. But it's this piece. It's factoring. To do factoring properly, I need to remember the key thing about factoring. Factoring is undoing the distributive rule, right? That means I got to be able to divide. What was the key property about being an integral domain? A commutative ring with unity that has
No zero divisors?
no zero divisors. And that's the piece I'm using. If I have two things multiplied together, then one of them must be 0. So if I can divide, that allows me to factor, then I can find roots easier because degree goes down when you factor something out, right? So I need you to remember for me how to do this. And for the moment, I'm going to make my life easy and work in the real numbers for my field.
Coefficient 2.
I'm sorry?
Is that first coefficient dx cubed? Is that a 2?
2x cubed plus 5. Yes, I have no variables up here. They're all numbers. I slashed my z's on purpose. Do you remember how to do this division? Yeah, that was my reaction too. All right. The way to do this division is to do it the long way. This is, by the way, the reason that doing long division by hand is still taught. I know everybody carries a calculator in their frickin' pocket. I'm never going to need to do long division. What do I do now? We'll pick this up on Tuesday.